Hello, my name is Kautilya and I would like to present our work titled LD-ZNet, Latent Diffusion Approach for Text-Based Segmentation. This is in collaboration with my mentors Bharat and Pallavi, my internship manager Beja, and my advisor David. To begin with, some of the discriminative retraining tasks such as image classification or captioning learns only the most discriminative regions of an image, such as face of a Mickey Mouse, instead of all the pixels of the Mickey Mouse. Moreover, the current datasets have a fixed set of categories limiting generalization to novel objects from internet. However, the recently introduced latent diffusion models can synthesize various objects at internet scale. We can also observe on the right that the LDMs contain enough semantic information to coarsely segment categories such as an astronaut or the Stonehenge. So it's interesting to see that LDMs can be used to get semantic information for novel categories across internet without needing any sort of pixel level annotations. So our problem statement becomes, can we use these latent diffusion models to improve text-based segmentation performance for different categories on various imagery, such as real datasets and AI-generated images? With that, let's look into our method on how to achieve this. We first begin with understanding few insights from the latent diffusion models, followed by our proposed architecture to improve the text-based segmentation performance. Firstly, the LDM operates in the Z-space of the VQGAN, that is a compressed representation of the image, which also preserves all the semantics. As you see on the top right, the Z-space preserves most of the semantic information during the encoding and decoding process of the VQGAN. Additionally, the LDM is pre-trained on the Z-space to generate different kinds of imagery ranging from AI art, cartoons, illustrations, etc. Thus, we propose to use this Z-space to train a segmentation network instead of the regular RGB images. Secondly, since the LDM can synthesize photorealistic images, it's natural to think their internal representations encode powerful visual linguistic semantic information of objects in the image and its caption. So we also propose to incorporate these powerful internal representations of the LDM into the segmentation network. Now let's take a look at our proposed architecture. Given an image and a caption, we use the Z feature of the image from the VQGAN as the input to the unit of the LDM and a similar unit segmentation network named ZNet. We feed the internal representations obtained from the LDM into ZNet through attention pool to eventually predict a binary mask. We name this entire pipeline as LD-ZNet. More specifically, the extracted internal representations from the LDM are passed through a self-attention followed by a cross-attention with the features from the corresponding block within ZNet to encode the LDM features into the segmentation network. Next, we realize that the middle blocks of the unit at around the time step equal to 400 carry maximum semantic information required for a text-based segmentation task. Hence, we use these specific blocks and time steps while injecting the features from the LDM into our segmentation pipeline. Before taking a look at the results, let me introduce you the three models we trained on the Fresca dataset, RGBNet, ZNet, and LD-ZNet. While RGBNet uses only the RGB images to train the segmentation network, the ZNet uses Z features as its input. We use RGBNet as our baseline for all our experiments. Our final model, LD-ZNet, also incorporates the internal representations from the LDM in addition to the Z feature as input. We evaluate all our models and previous works on real images, AI-generated images, and other miscellaneous examples. When tested on the Fresca dataset, we see a gradual improvement going from RGBNet to ZNet to LD-ZNet, indicating the importance of both Z-space of the image as well as the amount of semantic information stored in the internal representations of the LDM. It can also be observed from the visual comparison on the right that LD-ZNet does well in segmenting the hanging clock and the castle better than RGBNet and ZNet. Next, we were mainly focused on understanding the generalization of text-based segmentation methods on AI images because of the traction the AI-generated content gained in the past couple of years. Moreover, several editing workflows such as in-painting requires precise segmentation of objects in the image. Thus, it becomes important to understand the generalization ability of the computer vision systems to AI content. Hence, we created an AI-generated dataset named AIGI that contains 100 AI-generated images gathered from lexica.org website and 214 object instances labeled along with their categorical captions as shown on the right. We also make this dataset public for future research in this direction. Moving on to the results on this AIGI dataset, we see a huge improvement of around 20% for LD-ZNet compared to MDTR in terms of the mean IOU metric. Visually, we observe that the two methods, MDTR and the recently proposed segment everything everywhere all at once, otherwise seen, fails to segment the objects, Mickey Mouse, Goblin, Vespa, and animals, because the pre-trained datasets of these two methods are limited in terms of the number of objects, and also these methods are prone to a domain gap to AI-generated images during test time. ClipSeg, on the other hand, uses clip internally that is pre-trained with global image text pairs matching. This ClipSeg can only recognize most discriminative regions of the object, such as face of the Mickey Mouse. However, our method LD-ZNet does well on all these examples and on entire AIGA dataset, thanks to the reduced domain gap in the Z-space and useful internal features from the LDM. We also observe that our method does well on multi-object segmentation on thing and stuff classes, indicating our method has a good understanding of the overall scene. Additionally, we also observe the benefits of our method LD-ZNet on animation images, celebrity images, and finally illustrations. Compared to RGBNet baseline, our LD-ZNet can extract better segmentations for guitar and panda in animations, celebrities such as Scarlett Johansson and Kate Middleton, and finally segmenting objects in illustrations. From this work, we saw that the generative models such as LDM, pre-trained on internet scale, has enough semantic information about objects from internet. Making use of such models can boost the performance of computer vision systems, obviating the need for annotating at internet scale. Moreover, with the recent trends in creating AI-generated content, it becomes crucial to evaluate the generalization abilities of existing computer vision systems to the AI imagery. Finally, I would like to end this talk with a thought for everyone to think about. Can the generative models aid in developing a GPT-like revolution in computer vision that can generalize to internet data? Something to think about. Finally, I would like to thank all our collaborators on this work, and thank you for listening to this talk.